Okay, so I'm recording this video lecture because the last class I had, I forgot to turn on my YouTube recording. So therefore, I'll be recording and posting this video so as to basically replace or just to ensure that, for those of you who are not able to meet during the lecture time, you can actually have this video to watch so that you don't miss anything, all right? So we're going to finish up on chapter 9 and then start chapter 10. Chapter 9, well, this particular topic is very important. Resonance is a very important theory, especially for those of you who plan to do organic chemistry. What you're going to find is that this theory will become very useful for explaining a lot of properties of organic compounds and the type of reactions that they will undergo. And that's all I'm going to say about that. I won't go into any details as to how it applies to organic molecule. I'm just going to introduce a theory here. Okay, so resonance, the theory, states that whenever you have a situation where two or more molecules can be, or I should say one molecule can be represented by two or more plausible structures, Lewis structures, but the only difference between them is the distribution of the lone pairs and bonding pairs of electrons. Basically, the true structure will be a composite or hybrid of the different Lewis structures, all right? So as an example of this, we're going to look at the Lewis structure for ozone, which is over here. And then there's another plausible Lewis structure for ozone, which is over here. And if you look at these carefully, you'll see that the difference between them would be, as we said before, the positions of the electron pairs. So you'll notice, for example, that this oxygen here has 6 lone pairs and 1 bonding pair, but that same oxygen over here has 2 lone pairs and 2 bonding pairs. And the opposite is true for this oxygen compared to this oxygen. You'll see also that there's some shifting of the charges where this oxygen has a -1 charge, that same oxygen has no charge, but this oxygen that has no charge over here is a -1 charge, all right? And in organic chemistry, we use pairs, we use arrows to show how the electrons can be moved in order to establish the other structure. So if this pair of electrons move here, you're going to end up with a double bond here. And at the same time, this pair of electron goes here, and you're going to end up with the lone pair here, all right? And it is necessary for this electron pair to move when this electron pair comes here, because the oxygen here cannot have more than 8 electrons on its outer shell, all right? So, as was stated here, if you can draw 2 or more structures that only differ by how the electrons are distributed, then the real structure will be a hybrid between these 2 structures, all right? So that's because, and experiments have borne this out, that it turns out that one structure or the other does not satisfy, especially when it comes to data determined by experimentation, all right? So that's basically what the resonance theory says. I could go into more detail about that, but for now, that's where we're going to stop, all right, as far as this is concerned. Okay, another thing I want to talk about here is bond lengths, but before we do that, let's talk about bond order, which is it's not a difficult concept to grasp. Bond order basically is a reflection of the number of bonds that exist between 2 atoms that are covalently bonded, all right? So a single bond, it says that the bond order for that bond is 1. For a double bond, the bond order is 2. For a triple bond, the bond order is 3. And then the bond length is a distance by definition, usually expressed in picometers, between the nuclei of 2 atoms joined by a covalent bond. Now let me remind you, 1 picometer is equal to 10 to the minus 12 meters, all right? So that's the relationship between the picometer unit and the meter unit, all right? So some examples are shown here. For example, the bond length for the hydrogen to hydrogen bond is 74 picometers. For oxygen, it's 121 picometers, and some other examples are shown below, all right? Now, it turns out that the bond length depends on the particular atoms in the bond and the bond order. And for us to see that, we have some different representative bond lengths and the corresponding bond, the bonds, specific bonds and their corresponding bond lengths. And we're going to talk about bond energy later on, all right? So that's for later on. So one of the things that the bond length is dependent on is the size of the atoms involved. And to look at that, if you compare, I want to find a suitable, okay, let's look at these bonds right here, right? These are all halogen to halogen bonds. So you'll notice that as you go from fluorine to chlorine to bromine to iodine, you'll notice that the bond length increases. And of course, that's because as you go down that group 7, as you go from fluorine to chlorine to bromine to iodine, the atomic size increases. So if the atomic size increases, then correspondingly the bond size will increase as well. Let me see if I can find another example. Let's look at the hydrogen halide bonds here from HF to HI. Now in this case, one atom is the same in all of these bonds, hydrogens, but we're varying the other atoms from fluorine to chlorine to bromine to iodine. And what do we notice? We notice that the bond length increases as well. So even if you're just fixing one atom of the bond and the other atom is varied, you'll find that the bond length will increase with the size increase of that atom, which is varied. All right? Okay. As we said in the previous slide, the bond length also is affected by the multiplicity of the bond or the bond order. All right? So if you look at, for example, this series of carbon to carbon bonds, single, double, triple, you'll notice that there's a decrease in the bond length, right? So basically what that tells you is that the greater the number of shared period of electrons between the two atoms, the shorter will be the bond, all right? And that makes sense because basically the more electrons that you have being shared between the two atoms, the greater will be the attraction of the separate nuclei for the shared electrons, and therefore that bond will be drawn closer to each other, or the atoms will be drawn closer to each other, and therefore the bond length will decrease. We see the same pattern here when you look at the carbon to nitrogen single, double, and triple bond. Again, the bond length decreases as the multiplicity or the bond order increases. You see the same thing happening here. Carbon, oxygen, double and single bond. Again, the bond order increases. Correspondingly, the bond length decreases. And you see the same thing happening here with the nitrogen to nitrogen single, double, triple bond. Again, as the bond order increases, the bond length decreases. So we see that, basically that pattern basically established when it comes to the relationship between the bond order and the bond distance or the bond length. Okay, so as promised, we're going to talk about bond energies. And in some textbooks, they call this the bond dissociation energies, which is the energy required to break up a bond, to break a bond between two atoms, all right? And this is for the gaseous phase, right? So this only applies to gas phase situation. So for example, to break a hydrogen to hydrogen bond, the amount of energy required is 436 kilojoules. Now, in the case of water, there are two bonds to be concerned with, the oxygen to hydrogen bonds, there are two of them. So to break one of them, this is the amount of energy required, and to break the other one, this is the amount of energy required. So even within the same molecule, for the same type of bond, breaking one will require a different amount of energy compared to breaking the next one. All right. However, what we have in the table that I showed you before, the bond energies that are provided are called the average bond energies, right? And this is the average of the bond dissociation energies for a number of different molecules containing a particular bond. So even though there's a difference between bond energies for breaking one particular bond in a molecule and breaking another bond of the same type in the same molecule, what was done to get the data in the table previously was they basically average these bond dissociation energies for the same molecule and for different molecules, all right? And that's how we get these values. Let me go back to the previous slide. That's how we get these bond dissociation energy values that are shown here for different molecules, all right? Okay, now one thing I want to say here is that bond dissociation energies are useful because they can be used to calculate the enthalpy change of a certain reaction, but there are some limitations with regards to its use and the accuracy of such calculations. All right, so what is shown here is a molecular model representation of this reaction. Let me do this. The reaction is nitrogen, nitrogen, plus hydrogen to form hydrazine, which is N2H4. And these are all gases. Very important. These are all gases. All right. Okay. So we can actually use the table of values that I provided in the previous slide to determine the bond dissociation energy. Well, actually, to determine delta H. That's the aim of this exercise, I should say, to get delta H for this reaction, right? So the key thing you need to remember is what the bond dissociation energies represent. The bond dissociation energies represents the energy required to break up a bond between two atoms, a covalent bond between two atoms in the gaseous state, all right? So the way we would go about doing this, and okay, this would be a bit of a challenge here. Let me go to my writing pad right here. So I'm going to rewrite the same equation here. N2 plus 2H2 to give N2H4. Ah. N2H4 gas. All right? Now, in order to solve this problem using the bond dissociation energies, the first thing I would advise anyone to do is to write down the full Lewis structure of each of these molecules, because you need to know what the multiplicity of the bonds in each molecule is, all right? And that's very important for us to determine the bond dissociation energy for the bonds based on the table that's provided. So in the case of the nitrogen molecule, the full Lewis structure would be this. In the case of the hydrogen molecule, it will be H bonded to H, and there are two of them. And in the case of the N2H4, the Lewis structure is this: H to N to H, single bond, N to H to H. All right? So we need to identify the different types of bond, and we need to indicate the respective bond dissociation energies. So for the nitrogen to nitrogen triple bond, let me go back to this here, go to the table. Okay, so for the nitrogen to nitrogen triple bond, the bond dissociation energy is 946 kilojoules. So going back to this here, this would be 946 kilojoules, all right? In the case of the hydrogen to hydrogen bond, that's 436 kilojoules. So let me go back to here. So this would be 436 kilojoules, all right? Now, in the case of the nitrogen to hydrogen bond in the hydrazine molecule over here, you'll notice that there are four of them, right? So for each of them, go back to the table here. For nitrogen to hydrogen, that's 389 kilojoules. So this will be 389 kilojoules. And for the nitrogen to nitrogen single bond, going back to the table again, nitrogen to nitrogen single bond, that is 163 kilojoules. So this is going to be 163 kilojoules, all right? Okay, so the next step is to determine the bond, not the bond dissociation energies, the enthalpy change for the reaction based on the bond dissociation energies. So how do we do that? Well, what we do is that we take the sum of the bond dissociation energies of the reactants, and we subtract from that the sum of the bond dissociation energies of the products, all right? So in the case of the reactants, it's 946 kilojoules plus 436 kilojoules. And in the case of the products, now this is where you have to be careful. Oh, by the way, I made a mistake just now. Because of the 2 here, that means you have to multiply this here by 2, all right? So that's very important. Now over here, you have to take into account the coefficients when you're doing these calculations. Now over here, as I said before, you have 4 nitrogen to hydrogen bonds. So as far as the NH bonds are concerned, you have to multiply that by 389 kilojoules. And let me put this in square parentheses so that we can make a distinction between the sum of the bond dissociation energies for both the reactants and products. So for the nitrogen to hydrogen bonds, it's 4 times 389. And then for the nitrogen to nitrogen single bond, that's 163 kilojoules. All right, and then we just do the arithmetic. So for the reactants, it's 2 times 436 plus 946. And according to my calculations, this works out to be equal to 100. I'm sorry, 1,000. What am I doing? 1,818 kilojoules. And then for the products, it is 4 times 389 plus 163. Okay, so according to my calculation, this part works out to be equal to 1,719 kilojoules. And then let's see here. So 1818 minus 1719. So according to my calculation, this is equal to 99 kilojoules. All right. So that's basically how you use the bond dissociation energies to determine the enthalpy change of a reaction. Now, as I said before, there are limitations for this use of bond dissociation energies. And let me see what I have here. Oh, okay. So basically, the limitation of using bond dissociation energies for this purpose is that this only works well if the reaction is totally gaseous, if all the reactants and all the products are gases, all right? So that's basically the key thing you need to remember when it comes to using bond dissociation energies to calculate the enthalpy changes of reactions. If the states of the different substances are other than gases, in other words, liquids, solids, or aqueous, then it turns out that it's not as good an approximation when you're using this method. All right, so that's the limitation of using bond dissociation energies for calculations of the enthalpy changes of a reaction. Okay, so that's basically it for this chapter. And I'm going to stop the video here, and I'm going to move on to chapter 10. All right.